Today's objective is to learn how to write Verilog modules using gate primitives. So gate primitives such as and, or, not. What we'll do is we're going to take a Boolean equation and translate that to a Verilog module. We'll then later instantiate the module. Right, we'll see that that's equivalent to using a block symbol if you're doing a schematic interpretation. We'll also run a functional simulation of our modules to verify that they work. And then we'll use an RTL viewer to show the hardware that's actually synthesized in our design. Right. So the function we'll use today is our output f is a function then of 3 input variables a, b, and c. Right. And you could write that in one of 2 forms. If we specify the sigma notation with the 0, 1, 5, and 6, we know that in our truth table, rows 0, 1, 5, and 6, or the binary equivalents to the decimal number 0, 1, 5, and 6, will produce outputs of 1s. Alternatively, you can write it with product notation, and 2, 3, 4, and 7, those rows specify zeros. So you can write it in either one of these forms. I've just included both here, right, to tell us where our 1s and zeros are. What we'll do is we're going to create Verilog modules then for 4 different circuit forms: a canonical sum of products form, canonical product of sums form. We'll see the minimized sum of products form and minimized product of sums form. We're just going to do 4 different modules to give us practice in writing these, right? But we will start one at a time. We'll start with a canonical sum of products so that we can get right into that and see how to write that Verilog module. The others will just give us practice, and then we'll put them all together into a top level design where we create an instance of each module. Right. We're not deriving the equations here, just giving them, right? I have other tutorials then explaining how to derive equations, but canonical sum of products form, right? That's where you solve for the 1s of the circuit output. And we write these in Minterm form. So you can see that here in our equation, this first term here, A naught, and it with B naught, and it with C naught would be Minterm 0, right? And you can see here, Minterm 0 should have a 1. So remember, when you write a canonical sum of products form, you are going to include all the terms that produce 1s. The next term, right, A naught, B naught, C, that's the Minterm for 1. Here's the Minterm for 5 and 6, right? We won't go, like I said, go through these. I have other tutorials that do that. So in addition to that, here's our minimized sum of products form. We'll work with this equation. We'll refer back to this when we need to create it. Right. We've got then also our canonical product of sums equation here. And that is solving for all the zeros. Whenever you write the canonical product of sums form, you use max terms. So this is max term 2, 3, 4, and 7. And then I've already gone ahead and come up with a minimized product of sums form. Like I said, this tutorial is about writing Verilog modules and not doing the minimization. Right. When we write our Verilog top level module, what we're going to do is we're going to create something that's equivalent to, if we drew schematics for each one of those modules, so canonical product of sums, which I've shown in another tutorial, which I can link down below in the description, right? Often after we write a circuit, we create a circuit, we can create a block symbol of that circuit and use that symbol elsewhere in our design, right? So this symbol, Canon POS, symbolizes in the circuitry that we've drawn in a schematic for the canonical product of sums. And this is in a top level interpretation. I'll actually show you that in the project. So let's get actually out of these slides, right? And go ahead and take a look at some schematic equivalents. All right, and make sure you can see this here. Let me boost this big. All right, I'm using Quartus Prime Lite version 18.1 for this demonstration, and I've already drawn a schematic of each one of our equations. So this is our canonical product of sums form, right? Here in the using the text tool, I've just got a reminder that the function says, right, it should be the sum of Minterm 0, 1, 5, and 6. And we've got our inputs A, B, and C here on the left. So we've specified our input pins. We've got 3 NOT gates to generate our signals A naught, B naught, C naught. And then I'm using named wire connections, right? Named each one of these wires here right? And over here on the AND gate. So product of sums, right? The AND gate forms that product form. And so we would have then this AND gate here for minterm 0, where we've got A naught, and it with B naught, and it with C naught. The output of that AND gate then flows into an OR gate. So the product of sums, the OR gate is the summing gate. So each one of these AND gates flow into that OR gate. And notice I've labeled each one of the wires here, minterm 0, minterm 1, minterm 5, minterm 6, just to, when we write the Verilog, this will give us some help in translating that to actual Verilog code by naming these wire connections. And then of course we've got our output F over here on the right. So let's just, what we're going to do then in Quartus, if we want to write Verilog, is we're going to go to File, New, and we're going to tell it we want a Verilog HDL file, HDL for hardware description language. All right. A lot of times I like to write a comment in here. So I'm going to do a multi-line comment, and I'm going to start that with a /*. That's the beginning of a comment. All right, we say F of ABC is equal to the sum of our circuit with 0, 1, 5, and 6, if I remember correctly. Right. And * ends that. Right. And so I just want a reminder of where the ones of our circuit should be. And what we're going to do now is we're going to then get into the Verilog syntax. I'm just doing a double check, 0, 1, 5, and 6 to make sure that I remember that correctly. All right, so whenever you write a Verilog module, you begin with a keyword module. All right, so you can see as I typed it, it was in black, and as soon as I hit the space key, this turned into blue. Here, using Quartus, or if you use some other text editor program that understands Verilog, so a file with a .v extension in a programming text editor that understands Verilog will then show your keywords in a different color. Here in Quartus, our keywords are going to show up in blue. And keywords means that this word has been defined by the language to have its own special meaning, and we should not use it when we create our own identifier names. Right. So after we started with the keyword module, we have to give our module a name. Right. You can name it anything you want. I'm going to call this Canonical Sum of Products. So Canonical Sum of Products. Whenever you name a module, you create identifier names in Verilog. Start them with an upper or lowercase letter of the alphabet. Verilog does allow you to use some special characters such as an underscore or $sign. We're not going to start anything with a $sign. You can use within the names, you can use numbers, you can use the underscore, and you can use $signs as well. Like I said, $signs we will not use. All right, so after we've named the module, then what we do is we create a port list. So the port list then goes in between parentheses. So left parenthesis, and in the port list, you specify your inputs and outputs. So I'm going to say input wire A, B, C. So input tells Verilog the direction of the signal names that we put in the port list. So A, B, and C are signal names. Right? Wire, you can think of wire as, if you program in any sort of language, wire is a type. It's a data type. Now we're working with hardware. Wire says that these actually make actual physical hardware circuits, and you want to always have wire types in your port list. If you don't include the keyword wire, it assumes it's wire. In other words, if I just say input ABC, it's going to make the type wire. There are other types in Verilog, such as int, reg, float, other types like that are more advanced uses. I always encourage my students to say input wire so that they realize that this is a wire type as they're learning, right? After that, right, you specified the signal names. Notice then I separated them with commas. So A, B, C. You don't have to have the spaces. I'm doing that here for readability. So everything I keep typing after this would be assumed to be an input. And it is 1 bit by default. If we don't specify size, and we won't this, all of our inputs are 1 bit. in other tutorials, we'll show how to specify size. After that, then if I want to specify our output signal, comma, output wire F, right? I have no other outputs in the signal. So I'm just going to go ahead and give it the closing right parenthesis. And then you must put a semicolon at the end of the port list. And so what I'm going to do is here, I'm going to put another comment. So another way to create comments is 2 forward slashes. After that, everything on the same line is considered a comment. So a comment is just ignored by the programming tools. It's not going to be included in your design. These are just human readable comments that help us understand. So we always start with, right, module name, parenthesis, port list. That's what we've just done here. All right, as a reminder, every module ends with the keyword end module, END-MODULE, right? And so all of our code then goes in between module and end module, right? So what we're doing is, if I pop open that schematic right here, right, and if I even want to create a comment here, basically, right, we want some output F to be equal to minterm 0, ORed with minterm 1, ORed with minterm 5, ORed with minterm 6. That's what we drew in our schematic. And if we look at the fact that, well, minterm 0 is A0, B0, C0, that tells us then, right, here we've got our signals A, B, C, and F, but we don't have A0, B0, C0. So just like in the schematic, right, when we included these NOT gates, in Verilog, since we're using the gate primitives, we need to include the NOT gates. And so let's just say create internal wire signals. And what we're going to do is, and this is usually indented following. So that's not required for the syntax, but programming convention says to indent to make things more readable. And so signals that are internal, these are going to be of type wire. And then I'm going to call that A0, B0, C0. You could use lowercase. I'm using uppercase here to potentially make this a little bit readable. So now I'm creating these signals. Right? Now that I have the signal names, right, again, that equates to the fact that I named these wires here. And these named wires are the output of these NOT gates. So the input of this NOT gate is A, the output is A NOT. And now, right, we're going to add 3 NOT gates to create inverted outputs. Right. So in Verilog, the NOT gate is specified by the keyword NOT. And whenever you use it, so there actually is a Verilog Gate Primitive Module called NOT. And notice here in Quartus, right, everything that Quartus laid down, if I make that a little bit bigger, you can see everything has a unique instance number. So the first thing I put on this schematic, Quartus labeled INST. The next NOT gate, it labeled INST1, INST2. So Quartus just tends to use INST, right, followed by a number. So everything in a design has to have a unique instance identifier. Right? And so we could say the same thing here. We could say INST. And so this identifier name, right, again, start it with a letter of the alphabet, upper or lowercase. It can include numbers, and usually you don't see them whether there's special symbols in here. So you can use INST, and I'll probably do that now to remind you that that's an instance number. Sometimes I do things like if this is a NOT gate, I'll just say like N0 for my instance of my NOT gate. So these have to be unique, but so we'll just say INST 0. And then in parentheses, to connect to that NOT gate, the first thing we write is the name of the NOT gate output. A naught is our output, our input, then is A. We finish this off with a right parenthesis and a semicolon. That is the equivalent then of having put this NOT gate on a schematic. You said with Verilog, these gate primitives, the first signal in the list is the output. So this NOT gate will generate an output using signal A as the input, and this will be named A naught, just exactly like it is in our picture here. Right. And let's do the same now for B naught and C naught. So I'll call this, here's our NOT gate, INST1, B naught, comma, B, semicolon, not INST2, C naught, C. All right, now we have then gates producing those signals A naught, B naught, C naught. We can go ahead and create Minterm 0. And that is done with an AND gate. So again, here in our schematic, you see Minterm 0, we have a 3-input AND gate. It's got these 3 signals, A naught, B naught, C naught, and its output is named Minterm 0. Name of the gate, INST, let's call this 3. Name of the output, I'm going to call this Minterm 0. The input is A naught, B naught, C naught. Right, the inputs can be in any order. We could have said C naught, A naught, B naught. Remember, and logic is commutative. But once again, with all these gate primitives, the first signal in the list here is the name of the output. Now this output does not exist. So let's go ahead and create other internal wiring signals. So wire, Minterm 0, Minterm 1, Minterm 5, Minterm 6. And if you make these names descriptive, it makes your code a little bit easier to read. Again, if we go back and we equate this, right? That's why I named this wire coming out of here. And when we say internal signals, let me maximize this. So when we say internal signals, right, they are internal to this schematic. The only things that connect in this design to the outside world or the world outside this circuit are the 3 inputs, A, B, and C. That's what the circuit requires, some connections from the outside world whenever you use this for A, B, and C. And then it generates one output to the outside world, F. Within the circuit, then we name these other wires. So this is why I'm calling them internal wiring. Right, within this circuit, not connecting to anything outside the circuit, we have A naught, B naught, C naught, we have Minterm 0, Minterm 1, Minterm 5, Minterm 6. And that's how we make the connections, right, from one module to the next. So in Verilog, we then do the equivalent of using the keyword wire and specifying these names. And when you have more than one on a line, you comma separate them. I could have put all these on the same line. By default, the size is 1 bit. All right, so we've got our Minterm 0. Let's go ahead and then, right, Minterm 1, well, that's the signal A naught, B naught, C. So we do an AND gate, INST 4, Minterm 1, and A naught, B naught, C naught. Verilog's case sensitive. If I were to type C naught like this, we would get a warning when we go ahead and run analysis and synthesis saying implicit declaration of this this name CNOT because it's looking for a signal capital C, all caps. So you have to exactly match. Verilog is case sensitive. So whatever you name it here, use it consistently everywhere else. Right. If not, it should generate a warning. When you get warnings, you need to pay attention and correct those warnings. All right, so there's Minterm 1, right? Let's do the same thing for Minterm 5. Minterm 5 would be A, B not C. So and INST 5. Minterm 5, A, B not C. Finally, Minterm 6 is A, B, C not. Scroll up. INST 6, like I said. Minterm 6, A, B, C not. All right. So Verilog, right, just knows to create a 3-input AND gate if we have 3 inputs here. If we have, for example, if we only needed an AND gate with 2 inputs, if we just put 2 inputs here, it's going to create a 2-input AND gate. So let's go back and correct that. We'll see that when we do the circuit minimization. So once again, always with the gate primitives in Verilog, the first name here in this list then will be that gate's output. Everything to the right will be inputs to that gate. All right, that is the end of our, well, no, it's not the end of our module. Sorry, we've got our NOT gates, we've got our AND gates. The last thing we need to do is we need to OR all of those terms together, right? Our final circuit output here, this OR gate. Then notice then we had all of these minterms flowing in. So the inputs to this OR gate are minterm 0, minterm 1, minterm 5, minterm 6. Right? The output from that OR gate would be our signal F. Right, so we've created our products. Let's sum the product terms, right? Or sum the minterms. Or INST7, and our output is going to be F, and then our inputs we said are minterm 0, minterm 1, minterm 5, and minterm 6. All right, and so that's going to connect then to that output out. That should be our entire circuit. What we want to do is I have not saved this. So I created this Verilog file in Quartus. If I just save it and use the given name, Verilog 1, Quartus will not be happy. Quartus requires that I save the file with the same name as what I named the module. So I usually just do a copy paste. So let's copy that. Let's say file. Save. The first time I'm saving it, Quartus is going to come up and ask me what I want to save it. Actually, it's trying to save it with the name of my top level design. I don't want that. I'm just going to use Control V to paste this in, Canonical SOP. And notice then right here, this is part of my design. I'm going to right click and make this the top level entity so it will compile against this. And I'm going to run analysis and synthesis. So analysis then looks at our Verilog code. It's going to look at this and it's going to say, do I understand everything? Right. So it's going to parse through. And did I make any syntax errors? And then the synthesis step says, we'll take this English-like description, right? This type description, this Verilog description of our circuit, and synthesize it to equivalent hardware. Of course, we're going to expect to see the equivalent hardware being AND gates, OR gates, and NOT gates. Right, so good. I didn't get any errors or warnings. Right. And if you want to see then the actual hardware that you use, since this is the top level, we can go to Tools, Netlist Viewer, RTL Viewer, and put it up on the other screen. It usually takes just a second. Since this was the top level, right, you can see then the circuit it created, right? There's our module name, Canonical SOP. And look, here's for AND gates. That's what we'd expect. The bubbles mean then inversion. You can see our inputs here, A, B, and C. And if we click on this to the left, you want to see a little bit more about, right? It'll even show you the instance numbers here, shows you your ports, the direction, right? Input and output, right? Which is readily apparent from looking at the schematic generally. But if sometimes this information can be helpful here on the left. Okay, our three inputs, A, B, and C. The bubbles mean inversion. So right here, this is A naught, this is B naught, this is C naught, just as we specified. You can see then that the outputs of these gates are flowing into an OR gate and finally to our signal out. So what I like about the RTL viewer is to take a look at the schematic representation that it uses, especially as I get deeper into Verilog and I'm not using the gate level primitives, I'm using more of a behavioral description. I like to see then the circuits that it creates. It can be helpful in troubleshooting occasionally as well too, when I'm looking at that Verilog code and thinking it's doing what it should. Sometimes looking at this picture, I can see where typically it helps me see where I've got a bad connection, right? Something I didn't mean to connect. All right, so that's how to use the RTL viewer then. So we've got this canonical sum of products. If we wanted to create then a top level design where we actually instantiated the circuit. So let's go back to the schematic here. Let me just go ahead and reattach that to the project. So we've seen in other tutorials that when we create a schematic, we can create a block symbol of that schematic, which I've already done, but we can say file with this active, create, update, create symbol file for current file. It's going to come up and ask me what I want to name it. It already exists, but it uses the name of our file, which is canonsop.bdf for block diagram format. It's going to save it with a BSF, block symbol format. I'm just going to say save, right? It already exists. Do I want to replace it? Yes. Okay. And then we can then use it elsewhere, right? I've already created a schematic called top block that was created then by placing symbols that we had created. So canonical SOP. If I wanted to add that symbol into a schematic, right? Oh, we know that we right click symbol, our symbol window comes up under project. This is where it's going to store those block symbol files. Well, Canon SOP, if I grab that, add that to my schematic, then I've created an instance of this circuit, right? The block symbol was named Canon SOP. Notice it has an instance number. And here it shows then the inputs here on the left, A, B, and C, and the circuit output on the right. We don't know anything about how this circuit was formed when we use it, but if we do know that it was formed in accordance with our specifications for that function, that f is a function of A, B, and C, produces ones for 0, 1, 5, and 6, zeros for 2, 3, 4, and 7. So we do know that. So this is what we call sort of that black box or abstract interpretation of the circuit. We don't need to know how it was implemented. We just need to know for what the outputs will be for the given inputs whenever we use it. And that saves us recopying that circuit elsewhere by creating a block symbol and being able to use this block symbol in our design. We want to do the Verilog equivalent of that now. I'm just going to delete this here. And in order to create then the Verilog equivalent of that, we need to create a new Verilog file. So I called this top block. I'm going to say, all right, file new. Let's get another Verilog file, say okay. And I'm going to say file, save as. I'm going to call this top Verilog. It will add a .v extension for Verilog. And this is going to be my top level Verilog module. So again, this needs a keyword module. And since I saved it with the name top Verilog, I'm going to name the module the same, top Verilog, because Quartus won't like it if I don't. And again, I'm going to specify inputs, outputs. input wire, A, B, C, output. Output wire. Here I'm going to start with one signal, C, SOP. So for canonical sum of products. I could have called that F, but I'm going to end up putting other symbols in here, and we're going to end up with other outputs. Say, so for canonical sum of products, canonical product of sums. So let's just start with a 1. And module, a lot of times I like to type my end module right away so I don't forget. Sometimes if I get typing away, I forget. And then when I compile, right, Verilog tells me, oh, you forgot it. Gives me an error. All right. So we're going to create an instance of the module canonical SOP. When you do that, and a lot of times what I like to do is I like to just go back here to my module, and I just like to copy paste the name of the module and the port list. And I'm going to put that in a comment. All right. And the reason I do that is I want you to see whenever you create an instance of a module, the other terms are instantiate the module. So in order to instantiate the module, we use its name. So the module name is canonical SOP, right? And then you have to give it an instance number. I'm going to say this is INST0, right? I can start with the same instance numbers and reuse them here because I am in a different module, right? So this is unique to this design. And now I need to say what I want to connect in this module to the other module. And so here I want to connect, then the other module signal names are A, B, and C. And a name connection says to use the name of the signal in the module I'm instantiating, so .A. Maybe actually to make it a little more clear, maybe I'll just call these A, B, and C here, because they don't have to have the same name. So I'm going to use lowercase in this module. So when I say .A, that refers to the A input of the module canonical SOP. And I want to connect then my little a, the input from this circuit, to that. So that is the same as wiring input A, this module's input A, to this symbol, to this module's A. That is the wiring. Oh, didn't want to minimize that. All right. And top barrel. So I was here. Then we separate in the port list by commas .b. So I'm going to connect little b from this module to the capital B, and .c, little c to this. And then the other module's output is named F. So to F, I want to connect my canonical sum. I don't know what I hit there to destroy everything. All right. So with these name connections, you use the period, the dot operator. So .a, and you specify the name of the signal in the other module. That's this A. And then in parentheses, you say what you want to connect from the module you're working in. So I want to connect this signal A to that one's A. Then use a comma to separate the list. .b, named instantiation. So what I want to connect to B in the other module is I want to connect this signal's B, comma, right? .c, what I want to connect to the other one. So I'm naming the signal in the other module. I'm naming the signal in this module that I want to connect to. And then in parentheses, I'm using the name of the signal within the module we're currently working in to connect. And so to that outputs F, I'm going to use this one's canonical SOP. And right, this whole then list gets included in parentheses there, ends with a semicolon. Right. And we call that, right, named connection. You can use ordered connection, but I have students not use that in my courses because I want them to be very specific about what they're connecting, because it really typically helps with troubleshooting later on. Ordered connection, right? I would do the same thing in canonical SOP. So I use the name of the module I'm instantiating. I give it some sort of instance number. And then, right, I could just say A, B, C, C, S, O, P here. And ordered connection, then again, I'm using the names of the signals that I've defined in this module. I want to connect those signals. What it does is it uses order. So whatever I have first here in the list, it will connect to the first signal in the port list of the other module. So you have to make sure you get the order correct. And one of the things I don't like about ordered connection then is later I often have to go back and forth between modules to look to see, oh, well, what did this A connect to in the other module? Name connection tells me exactly what I've connected to in the other. And the other thing about name connection is you don't have to use the same order of the port list, right? If for some reason I wanted to connect B and C and then F and then later connect A, I could use a different order, right? Which can come in handy then when there are many, many signals in the port list to connect to, right? But my basic reason for using the named instantiation is it cuts down on troubleshooting. It tells me exactly then what I was connecting here. So in my examples that I use in my tutorials, I will use named connection instead of ordered connection, which, yeah, might be kind of confusing at first about which name is which, especially when they're the same. But I find in the long run with troubleshooting, maintaining circuitry, this works better. All right, so now we have created an instance of the module TSOP using named signal connection. All right, now I hadn't simulated the other. Let's just go ahead and make this top Verilog the top level. So right click, set as top level entity. Let's run analysis and synthesis on that. No, I don't want to change that top block. As a matter of fact, let's just close that top block. So it's building against this. All right, it's finished. Let's go back to the tools menu, netlist viewers, RTL viewer. And so now you can see that it built against this top Verilog is my top level module. Instances, it has one instance of this module canonical SOP, right? Which is why you're seeing then this looks just like that, or very close to that block symbol that we use in the schematic, right? Here's this modules A connected to top Verilog's modules A, right? So these port lists, right? These ports here, these are the ports of our module top Verilog, right? Input, output. You can see then here, these are the ports of this module canonical SOP, right? And so again, this looks just like that block symbol, that top level. If I double click on this, so when this is built on top of other circuitry, this is a symbolic representation of it. When you double click on it, then you can see that circuitry as well too, or simply select this and click on it. And this is what we saw before, right? So as my designs get more complex, looking at this RTL viewer is often very helpful to see the circuit interconnects. All right, let's just go ahead and run a functional simulation of this circuit while it's the top level. So I'm going to say File, New, and then I'm using then under verification debugging files, I'm using the university program BWF vector waveform. And it popped it up on my other screen. Let's just make this big here. All right, we're going to set our end time. We're going to go to edit, set end time. I'm going to do 80 nanoseconds. So 80 tab, type N for nanoseconds, hit enter for OK. Right click, insert node or bus, node finder, list. double greater than sign to select all of the all of the inputs and outputs. Okay, okay. So over here then, right, here's our output. Here are our 3 inputs from that top level module. I'm going to go ahead and say file, save. By default, this wants to give it the name waveform. When I've got multiple simulations in my files, I like to give them different names. You can see in this project, I already had simulated the top block. That was named sim top block. So I'm going to name this sim underscore top Verilog. I'm going to hit save. And I'm going to move my output. So I'm going to grab it and drag it down below. I'm going to select all 3 inputs. I'm going to right click and group those, form a group called input. And then I'm going to go up to C for the count here, for the count value. With all 3 of those selected, it's going to start at 0, increment by 1. I'm using that default 10 nanoseconds. Okay. So for an 80 nanosecond simulation, I have 8 unique inputs. You can see we're going to go from 000 all the way up to 111037 in decimal. Right. If you open this up, you can see then you could translate this to your truth table. If you've written a truth table where A is our most significant bit, C is our least significant bit. That's the way these equations were derived. I need to go to simulation settings. When I don't use the name waveform, then here, this is expecting the name waveform. I've got to then use, I'm going to delete this, and sim top Verilog was the name of my simulation. .bwf.bt. If I hit restore to false, then that changes the paths that are specified in this line up here off to the right. Hit save. If I say run functional simulation, it's going to prompt me, right? I've modified the simulation. I want to save it. Yes. And then we're going to run it and see what outputs we get. All right, which of course popped up on my other screen. Right. So we said this circuit was a product of minterms 0, 1, 5, and 6. I've got an error. Note then that we've got 0 is a 1, 5 is a 1, 6 is 1, 2, 3, 4, 7 are producing our zeros as outputs, but we're getting an output of 0 for our combination of 0, 0, 1. That's not what we expected. So I should have run that functional simulation before putting this in the top level module, but we'll just go back and let's check to see what error I possibly incurred with our canonical SOP. Oh, well, I used the wrong minterms, maybe. Did I use the wrong min? Yes. Oh, you're probably yelling at me in this tutorial. Minterm 1 definitely was not C0, right? I typed it correctly here, but not here. All right. I'm going to claim this is just a good way for you to learn how to troubleshoot by following my mistakes, right? But now, if I just hit Control S to save, I can just go back over here, top Verilog. We're going to run analysis and synthesis. We don't need to change anything in the top Verilog module, right? We've already made that connection. What it's going to do is it runs through here. It's going to go through the different design units in the project. And that means it will go through and take a look. And it's going ahead and looking at all the block diagram files in here. But you can see then, right, it found this design unit canonical SOP, meaning it reanalyzed it, it resynthesized that into hardware. And again, if we could go look at I should have noticed that in the RTL viewer, right? But I'm just going to go ahead and let's rerun the simulation now that we've updated and see if we get the correct output. Yes, 0, 1, 5, and 6 are ones. Our other outputs for 2, 3, 5, and 7 are zeros. So this module is now correct. All right, if you've stayed with me this far, you've seen then how to create a Verilog module using gate primitives. You've seen how to then instantiate it in another module, run a functional simulation, and use the netlist viewer to view your circuit. Right. I'm just going to go on. If you want to stay with me here in the video, we're going to practice by we're going to go ahead and create the minimize sum of products form next, and we'll create 3 more modules just for practice. So thanks for watching. I hope this has been helpful. Like I said, I'm going to stay with me. Let's go ahead and create some more modules for practice. So, all right. Yeah, let's go back to our minimize sum of product form. Let's just go ahead and implement this one next. So I'm probably just actually going to grab this equation so I can copy paste it. We're going to say file, new. We want a Verilog HTL file. I'm going to copy paste. Well, that didn't work. No, that wasn't straight from a text editor. So it was copying in symbols that we don't want. We want A naught, B naught, ORed with B naught, C, ORed with A, B, C naught. All right. And what I also like to put in is a reminder is f of C is equal to the sum of 0, 1, 5, and 6. All right, I always either want to know where my ones or zeros should be. So I find it very helpful to write a comment like this in here so I know exactly where the one should be. And I don't have to look at something like this and try to work backwards to figure out where my one should be. But I also like to put the equation in here that we're implementing so that as we troubleshoot our file, we can always refer back to it. All right, so keyword module. Name of the module, I'm going to just call this min SOP for minimum SOP form. Port list, you can leave a space, not leave a space. Port list begins with a left parenthesis, input A, B, C, output wire. Just going to call this one then F again. I left out the keyword wire. Like I said, if we don't put it in there, it assumes it's a wire. And module. And so we're going to need to generate A naught, B naught, C naught. Oh, we're going to need A naught, B naught, C naught. And let's just go ahead and do that. Not, so our not gate, instance 0. And then I'm just, remember, output first, A naught, input A naught. And this is something you can copy paste right from the other module so that you're not having to retype it. Here I'm retyping it, and I suggest as you're learning Verilog, you retype these so that you begin to put them into memory and you can look up less and less later on. And then later on, as you know how to do this from memory, that's when I use copy paste techniques, right, to speed things up. All right, so we've got our outputs A naught, B naught, C naught here, right? We want to go ahead and instantiate our AND gate. And so AND, I'm going to call this INST3. And that AND gate, our output needs a name. And I don't necessarily know that, let's see, min SOP. So over here, so here's our schematic drawing of the same thing, right? We've got our NOT gates generating those outputs. I named these wires coming out of these gates N0 and 1. I don't know, and N3. I don't know why I didn't call that N2, but these are the names of the wires. And that's what I'm looking for, is we need to name these outputs in Verilog because that's our way of wiring the output of the AND gate to the OR gate that we're going to create. All right. So let's go back here and I'll just call this N0. And then our inputs from our equation are A naught, B naught, And we need to go ahead and create those wires. I'm gonna call this and 0 and 1. I'm gonna call it and 2. And so for our next term, AND gate, instant 4. The output of that's going to be AND 1. The input to this one is B naught C. And our third AND gate, instant 5. Right? That output we're calling AND 2. It has inputs of A, B, C naught. And then that's going to flow into an OR gate. And instance 6, the output of that OR gate will be the circuit F. The inputs to that are AND 0 and 1 and 0 and 1 and 2. Right. That is our minimum SOP. I haven't put the comments in here. Like I said, if you've been using Verilog long enough, we likely don't comment these things, but I always tell students whenever they're new to this, right, as you're learning this, what really helped me is at first I didn't write comments, and later on I started putting in comments and things because I could go back and study this. If I put a comment in here that this was the name of the module, these were my port lists, that by default these signals were 1 bit, right? I could go back and look at these patterns and know what I'd done, why I'd done it. And then I could use that example to create a new example much faster than having to try to remember what I did before, like I said. But otherwise, then we typically don't put in those sorts of redundant comments. All right, let's save this, right, with the same name we used for the module. So file, save. I'm just going to paste that in SOP, save. Now we can make this our top level design and we can simulate it. But what we're going to do is let's just go ahead and create an instance of it in our file. So top Verilog, instantiate minimum sum of products module using named signal connection. Like I said, a lot of times the reason I like to copy the other is the port list is I've already got the name of the module. I can now say INST1. I've got the names here, so I can just say dot and I can fill in dot A, my little A here, dot B, my little B here, dot C, parentheses, my C, output wire F, dot, and here I want to then, I'm going to say MSOP for minimum SOP. So we're going to add then, this is going to generate the minimum SOP, eventually the canonical POS, and then the min POS as well. So I want to create those other signal outputs here. I'm going to save that. What we'll do is we'll go ahead and create our other modules, and then we'll run our functional simulation of all 4 of them at once. And now let's go back to, let's create another module. So file, new, Verilog HDL file. All right, this is going to then be our canonical product of sums. And we said the F of A, B, C. Now copy pasting comments here would probably be handy. Sum of 0, 1, 5, and 6. For product of sums, all right, we're interested where the zeros are when we write the max terms. That's a product of 2, 3, 4, and 7. Right. So I'm really interested in generating those max terms, and not so much, I'm interested in where the zeros are and not so much where the ones are. Of course, we know by default, if we know where the zeros are, we know where the ones are. And when we say this, well, this is the result of anding, right? Max term. So if we add and max term 2, hitting everything but what I want on the keyboard. Max term 3, 2, max term 4, 2, 7. Right. I was going to try to space those out to make them a little more readable. But we and the max terms together in the end. Again, if we look at the schematic that I've already drawn for that, which would be here, canonical product of sums form, and magnifying glass, right? You can see we've got our input signals A, B, and C. We have to generate our A naught, B naught, C naught. Right? Here are max term generations. The summing terms are the OR gates. So we're going to have a level of OR gates in our Verilog. These will be the inputs to those gates. These will be the outputs, max term 2, 3, 4, and 7. They will flow into an AND gate, which will generate our output F. Module, canonical POS, input A, B, C, output wire F. And I said, I could have copy pasted from the other. All right, let's go ahead. We're going to need A naught, B naught, C naught. Here's our instances of our NOT gates. And now let's generate, right, max term 2. And let's go ahead and create the signal name. So these are, again, I'm going to put a comment, internal signals, internal to this module. And we're going to, basically, we're declaring them. Term 2. Term 3, so that max term is an ORI, or INST3. Output goes first, so max term 2. Inputs to max term 2. Max term 2 is A, ORed with B naught, ORed with C. That's A, B naught, C. Right. Max terms generate zeros. Max term 3 is A, ORed with B naught, ORed with C naught. Right. So whenever you form max terms, any of the inputs that are ones get inverted, inputs that are zeros stay in their form. All right. So OR gate INST4. We'll term 3, A, B naught, C naught. Max term 4 here. Well, that's A naught. So A naught ORed with B, ORed with C. T5. A naught, B, C. Finally, max term 7 algebraically is A naught ORed with B naught ORed with C naught. So here, or INST6. Max term 7, A naught, B naught, C naught. And then our final gate, ending them all together. This is our F. Actually, this is our F of ABC is equal to this. Might have been a better place for this comment. All right, this is what we're doing here. We need an AND gate, INST7. All right, our output is going to be F, and then our inputs are X term 2, X term 3, X term 4, X term 7. Right. Just in the same way the wires were named in the schematic. And so let's save this. I'm going to copy this. Go ahead and make that the top level. I'm just going to tell it right now to make that the top level. We'll run analysis and synthesis to see if there were any syntax errors. And if we want to go ahead and create a, let's go ahead and do this. I'm going to close some of these other modules. Yeah, I thought. All right, so I didn't run that over here. This says I have a syntax error. HDL top. So what I like, a lot of times when it gives you an error, this is telling me the name of the module, top verilog.v, line 10. A lot of times when you double click, it will take you there, expecting a parenthesis and it got a semicolon. Sometimes they can be on the line above. Dot A, dot B. Oh, I'm missing the last parenthesis here. I often forget to do that. Right, while we're here, let's just go ahead and create, let's instantiate this module while we're there. And again, we're instantiate canonical product of sums module using name signal. Spelled module there. And so what was handy is since I copy pasted that, we're going to make this INST2. Right. And actually, I'm going to go for a little copy paste here. Right. And I want to connect canonical, so C POS, canonical POS to this. All right. There we go. Can't compile duplicate declarations of min SOP in the library work. I have more than one module. Oh, this is not happy with me because I named the Verilog module the same thing as the block schematic that's part of my design. Let's remove this file from the project. So it's going to remove it from the project environment. And let me name this minimum. Minimum SOP. So I had, like I said, a block diagram file with that same name. It didn't like the duplication. Now I need to save this module with this name. Save as V, and it add that into my into the project environment. Let's go ahead and make that the top level entity. Let's run analysis and synthesis on that particular module there. And of course, once I change the name there, back here in the top Verilog, this should throw an error because it now doesn't know that name. So this is now named minimum SOP. Might throw it. All right. So let's finally then create our minimum POS expression. File, new, Verilog file. And this is our minimized product of sums. And that expression is f of a, b, c is equal to a or equal to, I like put these on their own line sometime. Or with b naught and with b naught or with c naught, and that term is ANDed with a naught or with b or with c. All right, looks like I need a b naught, a c naught, and a naught. And let's get after some of that copy pasting here. So let's end our comment right here. Let's see. Module minimum POS. Input wire A, B, C, output wire F. Hopefully you're following along and practicing typing this stuff for yourselves, right? And you've got it working for yourself as well. All right, what did I just say I wanted to copy? All right, declaring internal signals. These are actually going to be or 0, or 1, or 2, because we're going to need 3 OR gates. But here's our NOT gates. All right, let's get after then those terms. So I need an OR gate for that first term, INST3. And we've got then, we're going to call that output or 0. The input to that is A, B, not, right? That is this term here. Another OR gate, INST4. That output will be named OR1. Its inputs are B naught, C naught. Third OR gate, INST5. That output will name OR2. And its inputs are A naught, B, C. Finally, we have the AND gate that we flow into, right? Because these 3 terms are being ANDed together. T6, and that output is F, and the inputs to that are the what flows out of our OR gates, so OR 0, OR 1, OR 2. That should be our minimum POS module. Let's save it. The same name as the module, and I do like to copy this over for later reference. I go back and look at this so I know exactly what my 1s and 0s should be, especially if I'm going to compare simulation results at a later time. All right, and let's then create an instance of this in our top level module. So top Verilog. I'm going to be lazy and do some copy pasting here. All right. Lazy. I can have errors when I type and I can have errors when I copy paste. So minimum product of sums. So this is minimum POS. Copy paste can get me in trouble with instance numbers, but I don't remember to change those. Signals are the same for the inputs, but MPOS for the output. All right. That was our goal then of instantiating each one of these, similar to what we've done with the block symbol. Let's go ahead and make this our top level again. And let's tell it to run analysis and synthesis against that. Hopefully we won't have any compilation errors. If there are, we'll correct them. And then we will run our simulation against that. But no, I have an error. So telling me it's a minimum file minimum POS.v line 9. Let's double click this. Text near wire expecting a semicolon. Oh, I misspelled output. So sometimes the messages aren't real helpful because this tells me text near wire expecting a right parenthesis. And I looked and I said, oh, well, I've got a right parenthesis. I've got my semicolon. So I have to ask myself, what should my port list look like? Right. And if I'm new to this, I often have to go back and compare it to a working port list. What I noticed was that, right, this was not highlighted in blue. I had misspelled output. So that was a real error, but the compiler couldn't tell that. Again, that looks like that was my only error. Let's run this. Sometimes when you're running analysis and synthesis, this will just quit. It won't after a certain number of errors because it just would keep generating more and more errors. So we always start it. If we have multiple errors, I always tend to start with the first error I'm given. Sometimes other errors come about because of that. Sometimes they don't. All right. So our analysis and synthesis work there. Let's just go to our simulation. And sim top block, sim top Verilog. All right, I want to bring in those other signals now. So I'm going to go to insert node or bus, node finder list, and I want to bring in, right, POS, these three signals that we've added since then, and add those on. Okay. Should be able to say Control S, save this, and then run functional simulation. And of course, we're going to expect all four outputs to look alike. Of course, it's possible that I've made an error. Oh, good, I did not. So all four of our circuits, right, they're all equivalent forms of the same function. They should all produce the same outputs. They're all producing ones for inputs of 0, 1, 5, and 6, and outputs of 0 for 2, 3, 4, and 7. Right. So we know then our Verilog implementation of all of those circuits is functionally correct. Close that down. Very last thing is, let's go to Tools, Netlist Viewer, RTL Viewer. And you can see now in this top level Verilog module that we wrote, right? Here's the RTL viewer gives us sort of a schematic representation. This looks very similar to that block diagram symbol representation. Again, if we click down on that, instances, you can see, right, we've got an instance of canonical POS, canonical SOP. You can see that as well here too. Each one of these blocks are named with their instances. Here's our inputs then to top Verilog, lowercase a, b, and c, our outputs, C, POS, CSOP, and so on. So if you want to drill down, you can double click on this, and there are the OR gates that were implemented. Here are the inversions, the bubbles are the knots, here are the AND gates. So like I said, a good way when you're writing Verilog is if you do understand the schematic representation. I know when I started with this, I was taught to draw things schematically first. So what I would do is a lot of times I would just sketch on a sheet of paper what the schematic implementation should look like. Go ahead and label my wiring connections and all, then write my Verilog based on top of that, my hardware description, and then use this RTL viewer after I got done writing it, then to double check that my circuitry looked like what I expected. Even when the simulation ran, I like to take a look at this. All right. So for students in my Logic Lab class, this should help you with your implementation of your lab assignment. And thanks everybody for viewing. Hope you found this helpful. If you have some other tutorials you'd like me to make, list below in the comments, or if you have any questions, I'll answer those as best I can as well too. Thanks for watching. Good luck with your designs.